Hi, everybody. Welcome back to Dave's Math channel. And this is my continuing feature on daily math problems, which I post every few days on the Facebook group Classical Mathematics. This is a recent one I posted a few days ago involving electric flux computing, electric flux through an equilateral triangle. So anyway, let's begin. So here's the problem statement. Here's also an accompanying picture. They say a picture is worth 1,000 words. So here's the problem. I'll just read it. We have a point particle of charge q at the origin and an equilateral triangle of side length L in a horizontal plane centered at distance d above the z above the particle, as shown for various values of z. I show 6 different values of z for these 6 equilateral triangles. I use different colors of the rainbow for each one. And these particular ones have z values of 0 0.3, 0 0.6, 0 0.9, 1.2, 1.5, and 1.8. And I guess L is 2 for this picture. So anyway, for each of these parts, I'm asking for the values of z in terms of L, such that the electric flux through the triangle is equal to each of these 3 different values. For part A, equal to q over 4 epsilon naught, part B equal to q over 8 epsilon naught, and for part C equal to q over 20 epsilon. And if you guys haven't had any courses in electricity and magnetism, then maybe this doesn't make any sense to you. I don't know. But if you know Gauss's law, that's the key thing here is Gauss's law of electricity and magnetism. If you know the theory, this is actually a pretty easy problem. And also if you use the right trick, which is symmetry in this case. So anyway, let me just go through the solution. So, here I give a definition of electric flux. Usually it's given in the Greek letter capital phi, and phi is defined as the surface integral. It's a double integral because it's the surface of the quantity E dot n, where E is the electric field, it's a vector, it's a vector field. So there's a thing called the electric field throughout space that's the result of charged particles. Charged particles all give off an electric field. In the case of a single charged particle, it's just a radial field, a lot like the gravitational field, except it's outward instead of inward, and its magnitude is proportional to the inverse. It obeys the inverse square law. It's inversely proportional to the square of the distance from the particle. That's what the electric field is. You don't really have to know that for this problem, though it turns out. And this n, this other vector, which I'm calling n, little n, is what's known as the unit normal vector. So in this case, it's going to be the n equal k. I'll get into that later, but it's going to be the unit vector upward because our surface is an equilateral triangle that's parallel to the xy plane, which means its normal is in the z direction. So anyway, that's what we have to calculate. And you could do this directly if you wanted, but it would be a pain in the ass because the electric field isn't in the z direction. You're going to have to, and it varies. It varies with distance from the origin. The distance of points in this equilateral triangle from the origin is not constant. It depends on where you are in the triangle. So you could do this, using this formula, but I wouldn't recommend it. I haven't done it this way, and this is not the most efficient way to do this by any means. So we'd like to find a trick to do this problem. Well, there is a nice trick, and the trick involves symmetry. First of all, if you look at Formula 2, Formula 2 is a very important formula here. This is known as Gauss's law of electricity and magnetism. Pretty amazing law. What this law says is that if you have a closed surface, then it's very easy to compute the electric flux through any closed surface. It just turns out that the electric flux, even though it's given by the same formula, it's a double integral. And here I'm using a circle for the integral signs. That just indicates that S is a closed surface this time. But it's the same definition of electric flux. But that turns out to be equal to Q, capital Q, over epsilon naught, where capital Q is now the total amount of enclosed charge. It's the total magnitude of the charge enclosed by S. And for the surface we're going to be looking at, that's going to be little q. And then we divide by epsilon naught. That's the formula. Pretty amazing formula. You could do the same thing for gravity if you wanted. I don't know if I've ever actually seen this law used for gravity, but you could, because the gravitational field is basically the same law, inverse square law, as the electric field, electrostatic field. Just a consequence of the inverse square law. But anyway, that's Gauss's law. And, maybe I should say something about this constant epsilon naught. It's a physical constant. It's known as the permittivity of the vacuum, or the permittivity of free space. And its value, in case you're interested in SI units, is 8.85 times 10 to the minus 12. The units are Newton meter squared per Coulomb squared. Anyway, that's epsilon naught. And now, so how do we solve this problem using Gauss's law? Well, the other trick is to use symmetry. And there is a lot of symmetry in this problem. It's a little bit in disguise, but think about platonic solids. I think you guys probably know about platonic solids. There's 5 platonic solids. They were discovered by Plato, I think, around the 3rd century BC. Plato was pretty amazing. But he discovered the 5 regular, they're sort of like 3-dimensional analogs of regular polygons, the regular polyhedra, if you like. And there's exactly 5 of them. They're the tetrahedron, the cube, the octahedron, the dodecahedron, and the icosahedron. But of those 5, only 3 of them have faces that are equilateral triangles, namely the tetrahedron, the octahedron, and the icosahedron. And it's no coincidence I actually designed this problem this way. Tetrahedron has 4 faces, octahedron has 8, and icosahedron has 20. And due to symmetry, if our charge, think we had our charged particle q, little q, at the center of each of these 3 platonic solids, what that would mean is that the flux going through each face due to symmetry is going to be 1 over f times the total flux. It's just the total flux divided by f, because each face has the same flux through it due to symmetry. So, for instance, if the total flux was, I think, well, I don't know if I give a name to it, but if it was phi total, yeah, I used the wrong symbol here. I should have used phi total, not s total. Yeah, phi total is going to be f times phi, or phi is phi total divided by f, where f is the number of faces. And that's exactly what we want. So, for instance, for the tetrahedron, it's going to be q over 4 epsilon naught, since f is 4. For the octahedron, it's going to be q over 8 epsilon naught, since f is 8. And for the icosahedron, it's going to be 20 over epsilon naught, since f is 20. And that's exactly what I was asking for. Let me just go back to that slide, the first slide, the statement of the problem. So, yeah, I mean, you see, for part A, I'm asking when the flux is q over 4 epsilon naught. For part B, q over 8 epsilon naught. And for part C, q over 20 epsilon naught. Those are exactly what we want, because those values 4, 8, and 20 are the values of f. And now, the only thing we need, the only other piece of information we need, is we need to know the values of z for each of these 3 platonic solids. And the value of z is really just the in radius. That's the radius of an inscribed sphere inside each of these platonic solids. If you think about it, that should make sense, because just imagine, I didn't draw a picture here, but just imagine that we're completing each of these 3 platonic solids. For instance, if the tetrahedron has 4 faces, imagine, so you're supposed to think of this equilateral triangle that we want to position right, being one of the four faces of a tetrahedron. So all we're asking here is to find, how high above the xy plane does this face have to be in order for this tetrahedron to be centered at the origin where the charge is. And that's just the in radius. So the in radius, I just looked these up on Wikipedia. The in radius of a tetrahedron in terms of the length of its side is just square root of 6 over 12 times the length of the side. And that's approximately 0.204 L. So that's the answer for part A. It's exactly square root of 6 over 12 times L, which is 0.2 over 204 L approximately, since that's the inner radius of a tetrahedron of side length L. And then for the octahedron, it turns out the in radius is square root of 6 over 6 times L, which is approximately 0.408 L. That's exactly twice the value for a tetrahedron. And finally, for an icosahedron, the value is, it's going to be a complicated analytic expression, square root of 3 times 3 plus square root of 5 in parentheses all over 12, and that's equal to approximately 0.756 times L. So those are the answers. That's how you solve this problem. You could do it the hard way. I wouldn't recommend it, but if you did it the hard way, you should get these same answers. And I guess the advantage of doing it the hard way, you could do it for general Z, not just these three specific values, because we relied on the symmetry of these platonic solids to get these specific values. But if you want to do it for general Z, you're going to have to do it the hard way, unfortunately. But anyway, that completes my video, my solution to this daily math problem. So thank you for watching. Long live math, and I'll see you guys next time. Bye.